Hi everyone, welcome to the Class 6 video lecture. Today we'll be talking about the constant acceleration equations of motion, which we started on in the last video, and we'll be specifically applying them to free fall. Okay, so let's get started with a quick review of one-dimensional kinematics. So remember we talked about displacement, velocity, and acceleration. So displacement is change in position, and it can also be measured as the area under a velocity versus time curve. Average velocity, remember, is displacement over elapsed time. So in other words, it's the displacement divided by the time it takes for that displacement to occur. And we can also measure the average velocity as the slope of the 2 points connecting the initial time and the final time on a position versus time curve. And next we have average acceleration. A average is equal to the change in velocity over change in time. Again, that change in time is just the amount of time it takes. Now it's for the velocity to change. And we can calculate the average acceleration as the slope of the 2 points connecting t initial and t final on a velocity versus time curve. Okay, and so now we're just going to remind ourselves of the simplifying notation that we used to define our 5 equations of motion for constant acceleration. So this simplifying notation, what we did is we just assumed, okay, we're just going to restart time at the beginning of our problem. And so we're always going to let our initial time just be equal to time t equals 0. Okay, and so then if we do that, we can use this shorthand notation of like x naught and v naught. And the naught just refers to these zeros here. And so really what that means is just the position at time t equals 0 for x naught, or the velocity at time t equals 0 for v naught. And so then we could say that the initial position x sub I is really just x naught. The initial velocity is really just v naught. Okay, and then once we have that, that settled, then we could just say, okay, so if my initial time is time t equals 0, then my final time, I'm just going to call it t. And so we just drop the final subscript on that. And we do the same thing for x and v. So we say, okay, so if it's not the initial time, it's going to be the final time. And so we say, okay, x final is really just x, and v final, we're just going to call it v. Okay, and so then with those simplifying notations, what we can do is we can actually just manipulate the 3 equations on the left-hand side of my slide over here and plug in the simplifying notation into those 3 equations, rearrange the equations in various ways, and we come up with these 5 equations of motion for constant acceleration. Okay, so let's take a look at using one of them to understand how the plot of position versus time should look when we have motion with constant acceleration. So first, let's just think back. What do we think the velocity versus time plot would look like when we have constant acceleration? So remember, the acceleration is the slope of the velocity versus time curve. So if the acceleration is constant, that tells me that my plot should have constant slope. So in other words, I should have a v versus t plot that is a straight line. Okay, so now let's think about position versus time. How do I think about this? Well, so what we want to do is think about our 5 equations of motion with constant acceleration, and I'm looking for one that includes x, which is my final position, and t, which is my final time, and then the rest of the variables in the equation are all just constants, because that's what's going to allow me to think about the shape of the graph of x versus t. So if I look at my list, the equation that matches that description is the one I have written here. So x equals x naught plus v naught t plus 1/2 a t squared. And this equation, if I think about it, x is on my vertical axis and t is on my horizontal axis. It looks a lot like the equation for a parabola that you would maybe have learned in math class, where we had y on the vertical axis and x on the horizontal axis. Then you probably learned that y is equal to a plus bx plus cx squared, where a, b, and c are just constant values. Okay, and so then what I could say here is, well, do these really match? They do match because x naught, that's your initial position. That's just a constant. It's not changing in time. V naught is your initial velocity. That's also a constant. It won't change in time. And A, we already said was constant in this particular case. And so what that means is that comparing these two equations, I would expect my position versus time plot for motion with constant acceleration to look just like a parabola. Okay, and specifically we can draw some comparisons between these two equations. So if I look at these two equations, I would say that the x naught in my position versus time graph is going to play the same role as the constant a in the mathematical equation. V naught, the initial position, should play the same role as b. And if I look at the coefficient of the x squared, c, I expect that 1/2 a will play the same role as c in my equation here. Okay, and so now let's take a closer look and see, what else we could tell. So we know that the position versus time graph for motion with constant acceleration, it should look like a parabola. Is there anything else that we can tell about it just by looking at our equation here? So it turns out that we can actually also tell whether the parabola is going to be curving upwards or like U-shaped, or whether it will be curving downwards. So I would say that's like rainbow shaped or something like that. And how can we tell? Well, it turns out that it's related to whether or not the coefficient of t squared is positive or negative. So the 1/2 is always going to be positive, which means for us, it's really going to be dependent on whether the acceleration is positive or negative. So let's take a look here. Example 1 in yellow is I have a positive acceleration over here, plus 1 meters per second squared. And the example I plotted in green has a negative acceleration. So based on this plot, what I would say then is that if I have a positive acceleration, a positive coefficient on my t squared, I should get something that's curving upwards, or mathematically we would say it's concave up. If you get something with a negative acceleration, then you get something that looks concave down, or it's curving downwards. And so that's going to be our relationship here. So if you have positive acceleration, you should expect concave up. If you have negative acceleration, you should expect concave down. All right, so now let's take a closer look at a specific example here. So remember from class last time we talked about a car approaching a school zone that decelerates at a constant rate from positive 45 miles per hour to positive 20 miles per hour in 20 seconds. So this means that it's going positive, it's moving in the positive x direction, right? So positive 45 miles per hour and positive 20 miles per hour. All right, so we want to know, is the x versus t plot, will it curve upwards or will it curve downwards? Okay, so how do I go about answering this question? First thing I need to think about is what is the direction of my acceleration, right? Because that's the thing that determines whether the graph will curve upwards or downwards. So how do I decide which direction the acceleration is? We want to remember that if the acceleration and the velocity are in the same direction, then the car will speed up. It'll start going faster in whatever direction it's going in. If the acceleration and the velocity are in opposite directions, then the car will slow down in the direction that it's going in. And so here I see I go from 45 miles per hour to 20 miles per hour, both in the positive x direction. And so if my car is slowing down, right, 45 down to 20, that means that my acceleration must be in the opposite direction. It must be in the negative x direction. So I have negative acceleration, which we just saw on the last slide, means that our position versus time curve should be concave down. So I would say here the answer is B. All right, so just a little recap on our equations of motion with constant acceleration. I will just reiterate here that they're not something that I would recommend memorizing. So I would recommend knowing that they are there and being able to find them. So have them written out on a piece of paper that you keep near you for when you're doing problem solving. But you do not need to memorize them. There are many ways to solve a particular problem. So don't worry if you see me solving a problem a particular way, or you see, your friend is solving a problem a particular way that isn't the same as the way that you did it. That's totally fine. There are definitely multiple ways to solve a particular problem. In general, though, there will be one way that's easiest, and that's the one where you look at, okay, look through your problem statement, write down everything you know, and make a note of the thing you're looking for. And then you want to look at these 5 equations and say, of the things that I know and the thing that I'm looking for, which equation will give me the thing that I'm looking for, because it has everything else in it are things that I know. And so that's going to be the goal for solving these problems. All right, and then one just last quick plug about avoiding the equation V average equals delta x over delta t whenever you're given just a velocity or a speed. So remember that the average velocity is not the same as the instantaneous velocity. So even though it's really tempting, I think because we learned that equation first, it's really tempting to just use that equation whenever you have a velocity and a time and you want to know position, or you have a position and time and you want to know velocity. But it won't always work, because oftentimes you'll be looking for instantaneous velocity and not average velocity. So that means you'll be looking for V and not V average. So just a quick plug, I would always recommend going to these 5 equations that I have in the blue box here. You can always plug in A equals 0, so that's the case where you're told the speed is constant. If the speed is constant, that means delta V is equal to 0, and so your average acceleration will be 0 as well. And so I would recommend using these equations in the blue box whenever you're looking for kinematics kinematics solutions. Okay. All right, and so now on to our specific application of one-dimensional kinematics here, and specifically motion with constant acceleration. It turns out that there is an example that we see all the time and experience all the time in everyday life, and it's called free fall. So free fall is just when you have an object and it's falling freely under the influence of gravity. Free fall was first studied, or at least first documented to be studied by Galileo in the 16th century. He dropped a musket ball, which is like a small ball, and then also a cannonball, which is much larger. Supposedly, he dropped them off the Tower of Pisa. So this is a bit of a myth, but perhaps he really did it. Who knows? So the story goes that he dropped them both off the Tower of Pisa, and they hit the ground at the same time. So this was one of the first documented studies of free fall, and we'll talk about what that means in just a moment. The next person to really contribute to the study of free fall is Isaac Newton, and this comes in the 17th century. The story for Isaac Newton goes that he was sitting under an apple tree, and an apple fell from the tree onto his head, which made him ask the question, why is it that the apple always falls down? Why doesn't it go sideways or upwards or, diagonal? Why does it always fall straight down? And he reasoned out that the earth must be drawing the apple to it, and so that's why it always falls down. Okay, and so these two things contributed to what we now understand to be free fall. So again, free fall, the motion of an object falling freely under the influence of gravity. Yes, I realize that that is a terrible definition because we say free fall in the definition of free fall. So let's take a closer look at free and fall in this definition. First of all, free just means free of anything other than the Earth's pull. The Earth's pull is what we refer to as gravity. So here we're saying we're free of anything other than gravity pulling on the object. Some example of things that, would contribute to an object not being in free fall. So some other things that in free fall an object must be free of would be air resistance and, friction, things like that. So whenever we talk about free fall, we're assuming that we're only looking at the earth pulling the object towards it. Okay, and then we have this word fall, which you might think, well, that makes sense. I understand what a fall is. Well, unfortunately, it's a bit of a misnomer here, actually, because when an object is in free fall, it doesn't necessarily have to be falling towards the earth. It can actually be moving upwards as well, because the free fall part is just whenever the only thing acting on it is gravity. So for example, if you have a ball in your hand and you throw it upwards, right after you release it from your hand, nothing is acting on it except gravity. So even though it's moving upwards, we say it's in free fall. Okay. And so what is free fall? What does this really mean for us? It turns out that in free fall, everything accelerates towards Earth's center, towards Earth's surface, with an acceleration of 9.81 meters per second squared. So we define this acceleration, we call it the constant g, and it's always defined to be positive. So acceleration is a vector, which means that we need to include our direction. So if you define downwards to be the negative direction, you would just say that the acceleration a is equal to negative g, so negative 9.81 meters per second squared. Okay, and then this acceleration due to gravity, g, it varies by location. So actually, if you think about like Denver, it's at a very high elevation, it's much higher off the Earth, and so then the acceleration due to gravity is actually reduced. But very close to Earth's surface, so like here in Cleveland, it's very close to 9.81 meters per second squared. Even in Denver, which is at quite a high elevation, it's still pretty close. It's 9.796 meters per second squared, so still pretty close. If we go to another planet, for example, or to the moon, as the example I have here, then this acceleration due to gravity would be due to that other planet or, solar object that we're talking about. So for example, on the moon, it's much less massive than the Earth, and so that means that it pulls objects to it less strongly than the Earth does. And so it turns out the acceleration due to gravity of the moon is only 1.62 meters per second squared. Okay, and then let's get back to this point that Galileo made with his cannonball and his musket ball. So this is the acceleration that every object in free fall experiences, whether it's a big object or a small object. So I think this might be a little bit counterintuitive. You might think if you have something that's really heavy that it would fall faster than something that's pretty light. And so it turns out that if you do not have drag, if you don't have air resistance, those two objects will always fall at exactly the same rate, which is the rate that is due to this acceleration due to gravity, 9.81 meters per second squared. Okay. All right, so let's do a quick example here. When Galileo dropped these objects off the Tower of Pisa, we want to know if they fall for 1 second, what would their new velocity be? What speed, actually? I'm just looking for speed here, so we don't need to include a sign. Okay, let's see how I approached solving this problem. First thing, I'm just going to make a few scribbles on the problem statement. So first of all, this is something that you will see a lot. They're dropped from rest, and so it's not explicitly telling you that the initial velocity is 0, like in those exact words, but that's what that statement means. So whenever you see dropped from rest or released from rest, something like that, that is always telling me that my initial velocity v0 is equal to 0. Okay, so that's that. Then we have, we want to know what speed, and so that's saying my final speed v is my question mark. Okay, and then we want to know, we still have the fact that we have the time frame here. So that's my final time is going to be 1 second if they're released at time t equals 0. So I would say t is equal to, 1 second. Okay, and then we're not explicitly told this, but we know that these objects are falling in free fall. And so what we know is that the acceleration, a, is going to be equal to 9.81 meters per second squared. And if I define downwards to be the positive direction, I could say plus 9.81 meters per second squared. Okay, and so that's another piece of information that you will not be explicitly told in the problem statement, but if it's free fall, then you should know to plug in that the acceleration is just going to be g, whether it's in the upwards direction or downwards direction, depending on, well, it's always in the downwards direction, but plus or minus depending on how you define your coordinate system. Okay, so from there, I think we're ready to solve our problem. I look at my knowns, so I have v0, I have time, and I have acceleration. I look at my unknown, which is v, and I look at that list of my 5 equations of motion for constant acceleration. And what I would pick is v equals v0 plus at. Okay, so I can plug in all of the information I know. I have v naught equals 0 because it's dropped from rest. I have a is equal to plus g because I defined down to be positive. And so then I can just plug in my 1 second as well, and I get that my final velocity is going to be 9.81 meters per second, and my speed would just be 9.81 meters per second. Okay, so I would say the answer is A. Next one, let's say now that we want to know what is the speed. Again, he's dropping these objects from rest, and we want to know what's their speed when they hit the ground if the tower is 55.9 meters tall. Okay, let's go ahead and make some notes on our problem statement again. We have that they're dropped from rest, and so again, it tells me that v naught is going to be equal to 0. I can also automatically write down we have free fall, so let's use A is equal to plus g again. And then we say what speed, so that means that the final speed is going to be the thing I'm looking for. And now I'm told the tower is 55.9 meters tall, so what is that really telling me? It's telling me the displacement of the objects that he dropped from the top of the tower to the bottom of the tower. And so if I defined downwards to be the positive x direction, then I would say that that is the displacement, delta x, and it's plus 55.9 meters. Okay, so now I have A, I have delta x, I have v naught, and I'm looking for v. This is missing time, right? So I want to use that equation that doesn't include time. So I would go ahead and use the equation v squared equals v naught squared plus 2a delta x. We can plug in v naught is equal to 0 because it's dropped from rest. We also plug in our acceleration and delta x as mentioned above. And then we can rearrange by taking the square root of both sides of the equation so that we get v, our final speed, is equal to the square root of 2g delta x. Plugging in our numbers, I get 33.1 meters per second here. Okay, and now let's just take a closer look at free fall. Specifically, we're going to study there's some really nice symmetry in free fall, and so we're just going to look at a specific example and study that symmetry. So here's the problem setup. Imagine you have a ball in your hand and you throw it straight upwards with some initial velocity. I'm going to go ahead and define the upwards direction to be the negative direction and the downwards direction to be the positive direction. So just in your mind, keep it in your mind that we have this like flipped coordinate system compared to what you would normally think of, which is upwards being positive and downwards being negative. So we flipped it here. Down is positive. All right. And so what that means for me is that my initial velocity, it better be negative, right? Since I threw it upwards, I threw the ball up. And so just to make that really explicitly clear, I'm going to say that my initial velocity has a magnitude of v naught, and so it would have a sign of negative, right? It's in the negative direction, and so I would say my initial velocity is equal to minus the magnitude of v naught. Okay, so then my ball, it's thrown upwards, it has a speed in the negative direction, the upwards direction. It has acceleration in the positive direction, which is the downwards direction. And so that tells me that the ball, as it's moving upwards, it's going to be slowing down, right? Since acceleration and velocity are in opposite directions. So what really ends up happening is it will slow down so much that for just a moment in time, it will actually stop in the air. And so this is going to be the peak height. So at its very highest height, it will actually stop just for an instant in time before it turns around and it starts to fall back down. And so this is something that intuitively, you can try it out, you can look at it, and you can see that this really does happen. Okay, so what questions do we want to answer here? First of all, we want to know what is that peak height, how high does the ball go, and then also how long does it take to get there? So to solve this problem, let's just make our list of knowns and unknowns. So first of all, this is free fall, so the first known I'm going to write down is A. I define down to be positive, so it's going to be plus g. Okay, then we also are told the initial velocity, remember v naught, is equal to minus the magnitude v naught. And then we also know that at the peak, remember the ball stops for just a moment, and so that's our final time. is at that peak. So v is going to be equal to the velocity at the peak. This is my final velocity. And we know that that is equal to 0. Okay, and so then what do we want to find? First of all, we want to find the displacement upwards. So that's the distance traveled from the initial location, right where it's released, up to the peak. And so specifically, I'm going to call this delta x up. And that's because we're also going to study this situation as the ball falls back down. Okay, and then we also want to know the final time when the ball gets to the peak, assuming that we have our initial time t equals 0 right after the ball is released from your hand. So that final time is the other thing we're looking for, and let's call that t up. So the amount of time it takes the ball to travel to the top, to the peak. Okay, let's start with delta x up. And how am I going to solve this? Well, if I look at my list of knowns and I look at my list of 5 equations of motion for constant acceleration, I would go ahead and pick the one that doesn't include time because I don't know time yet. And so what that means is I would start with the equation v squared equals v naught squared plus 2a delta x. So plugging in the information from our specific problem, our final velocity v is 0. This is equal to minus the magnitude v naught squared. So that whole thing has to get squared. So make sure you include your sign inside your parentheses because it's included in v naught. And so we have to make sure that we square the whole thing. All right, plus 2g for acceleration, and then delta x up, which is of course what we're looking for. Okay, so when I do this, when I do my squaring here, remember you have to square the minus sign and also the v naught. So minus 1 squared is just plus 1, and then v naught squared is going to be v naught squared, right? So that's not really changing. So what we end up with here is just the magnitude of v naught squared. So that minus sign cancels out. Plus 2g delta x up. Okay, and now we're ready to solve for, and this is still 0 over here. We're ready to solve for delta x up. So I have to subtract v naught squared from both sides and then divide by 2g. And so what I get here is that delta x up, it must be equal to minus v naught squared divided by 2g. And so does that make sense that we have a negative displacement? Yes, in fact, it does, because remember we defined the upwards direction to be the negative direction. So as the ball travels from your hand to its peak height, it's traveling up, which is the negative x direction. So good news that we got a negative value there. Okay, next let's calculate t up. Again, there are actually multiple ways that you could solve for t up at this point because you have lots of known quantities. If I look back at my original known quantities, a, v naught, and v, I would pick the equation v is equal to v naught plus a t, since it has only knowns and then also time, which is the thing we're looking for. So I would plug in my appropriate information here. My final velocity is 0. My initial velocity, remember, is minus the magnitude of v naught. Acceleration is plus g, and then we have time, which is t up. That's going to be the final time when the ball gets to the peak position. Okay, so now I can just go ahead and rearrange to solve. I add v naught to both sides and divide by g, and I find that t up is equal to magnitude of v naught divided by g. Okay, and good news, we got a positive value for time because time is always positive. So that's what we wanted. All right, super. So just to recap, at the top of the trajectory, the ball will stop for just a moment. So that v peak is going to be 0. And then we just calculated that the displacement of the ball between the place where you threw it and that peak position is going to be minus v naught squared over 2g. And the time it takes to reach that peak position is the magnitude of v naught divided by g. Okay, so when the ball reaches the peak, acceleration due to gravity is still pulling it downwards. And so what ends up happening, it stops for a moment, and then if you think about it, when you throw something up in the air, it'll stop and then it'll come back down. And so we want to now study this downwards trajectory. So what happens as it falls back down? Okay, so how do I do that? What questions do I want to answer? I want to answer the questions, what is the ball's velocity when it reaches the height from which it was thrown? And so when it gets back to the place that you threw it from, basically. Or in other words, it has traveled through a displacement equal to x down, which would be the same as x up, but in the opposite direction. So I would say that's equal to minus x up. We also want to know how long will it take for it to fall back down, and then finally, what's the total amount of time that the ball is in free fall, which would be the time it takes for it to go up, and then the time it takes for it to come back down. So let's start with this first question then, which is what is the ball's velocity when it reaches the height from which it was thrown, or in other words, when it has traveled through a displacement that is the same in magnitude but in the opposite direction compared to the displacement in the upwards direction, which we have in this blue box up here. Okay, so first, of course, let's make our list of knowns. First thing, every free fall problem, I'm going to write down that the acceleration is equal to plus g, since I defined downwards to be the positive direction here. Next thing is to make note of what am I defining to be my initial time t equals 0. So for this problem, I'm going to reset my time frame. So I want to make my initial time the time that the ball is at the peak. So when is the ball up at that peak location? So I'm going to go ahead and say t initial, which is equal to 0, is at the peak. Okay, and so then with this definition, I can define my initial velocity, right? So v naught in this case. Since my initial time is at the peak, my initial velocity is the velocity at the peak. And that, of course, is just 0. All right, and then what am I looking for here? Oh, sorry, no, we have one last known quantity, which is the displacement. So we want to know here this displacement, delta x, is equal to, we called it delta x down, which we're told is equal to minus the displacement upwards. So in other words, this is just telling us that the ball is falling from the peak back down into my hand. Okay. So that's all of our known quantities. Now let's write down our unknown, which is the velocity at the when the ball reaches your hand again. So when it falls through that same displacement. And so just explicitly here, I'm going to call that v final, since there's a lot of moving parts in this problem. So let's call that v final, the velocity when the ball reaches back to your hand. Okay, so looking at my known quantities here, I have delta x, I have v naught, and I have a. I don't know the final time, and so that tells me I'm going to use the equation v squared equals v naught squared plus 2a delta x. Plugging in the information from this problem, our final velocity, that's the thing we're looking for, v squared. It's equal to v naught squared. Remember, that's the velocity at the peak, since we redefined our time t equals 0 to be right at that peak. And so I have 0 squared plus 2. My acceleration is g, and then my displacement is delta x down, which is minus delta x up, which I can plug in using the equation in the blue box. So I'm going to say that that guy is going to be minus delta x up, which is minus the magnitude of v naught squared divided by 2g. Okay, so I have a minus sign multiplied by a minus sign that gives me a plus sign, and so I have 2g v naught squared divided by 2g. 2g divided by 2g, those two guys will cancel. And so what am I left with? I just have v squared is equal to the magnitude of v naught squared. Okay, I can take the square root of both sides of this equation. That will really only tell me the final speed. So whenever you take, when you take the square root, you only get the magnitude. The sign kind of disappears, and so you get v equals the magnitude of v naught. But just by looking at our, and this was v final, I should have written that, sorry. And so just by looking at our problem statement though, we can tell that the ball is traveling downwards, right? So when it reaches your hand, it's traveling in the downwards direction. And so that tells me that my velocity is equal to plus the magnitude of v naught, right? Since we defined downwards to be the positive direction, and this is final. Okay, and so what does that tell me? Well, it tells me that once the ball has been thrown up at an initial velocity of minus v naught, it travels up to its peak where it stops for just a moment and then it falls back down. And when it gets back to my hand, it has the exact same speed, it's just traveling in the opposite direction. Okay, now let's ask ourselves the question, how long does it take the ball to fall back to my hand? And then finally, what is the total time that the ball is in free fall? So let's list our knowns again. All right, so it's going to be the same list as last time. So we have A is equal to plus G. Again, we've redefined our time so that it's restarting at the peak. And so I would say T initial, which is of course the time T equals 0, is happening at the peak. Okay, and so then that tells me that my initial velocity, v naught, is the velocity at the peak, which is of course just 0. Okay, and we already know from the last problem, I'm just going to write down that v final was just equal to plus the magnitude of v naught. And so then I can use these pieces of information to solve for t, which is my final time. That's the thing we're looking for. And I'm going to call it t down. So this is the amount of time to go from the peak back down to my hand. Okay, so how do I solve this? Well, if I look at my list of 5 equations, I have A, I have v naught, v, and I'm looking for t. And so I want to use v is equal to v naught plus a times t. Okay, so plugging in our information here, I have v final, which is plus the magnitude of v naught, is equal to v initial, which was our peak velocity, so that's 0, plus g multiplied by t, which I called t down. Okay, so I can go ahead and solve for t down, and I get magnitude of v naught divided by g. So this is the amount of time it takes for the ball to go from the peak back down to my hand, and it should look awfully familiar, right? So if you look up at the top, this is exactly equal to the amount of time it took the ball to go from my hand to its peak. Okay, and so what does that tell me that the total time is? Well, the total time in free fall is from the moment it leaves my hand to the moment it comes back, and so that would be t up plus t down. And so that would just be 2 magnitude of v naught divided by g. So it's just double. Okay. All right, so let's just do a quick recap of all of the information we just learned. So first of all, our ball, it's in free fall from the moment it leaves my hand to the moment it comes back. And that whole time it's experiencing acceleration due to gravity downwards, which I said was the positive direction. So it's plus g. At the top, it will stop for just a moment, and so that tells me that the peak velocity is going to be 0. And then we know that the ball is thrown upwards with some negative v naught, and when it comes back down, it reaches the same point, it comes back to my hand. It has the opposite direction, but the same magnitude as it started with. And so I would say that v final is equal to minus v initial, which was of course negative, and so that means that v final is just plus v naught. Okay. We learned that the time it takes for the ball to go up is v naught divided by g, and this was exactly equal to the time it took for it to fall back down. And this assumed the fact that we were covering the same displacement. So it moved upwards a certain displacement minus v naught squared over 2g, and then we were allowing the ball to fall back down to the same location to my hand. Okay, and we can look at this symmetry one last way to kind of wrap up for today, and that's by exploring the position versus time, velocity versus time, and acceleration versus time graphs for free fall. So let's go ahead and do that, starting with the position versus time graphs. So position versus time, remember we want to use the equation that has final position and time, and then the rest of the variables in the equation are all just constants. And so that means we want to use x equals x naught plus v naught t plus 1/2 at squared. Plugging in our appropriate information here, we know that we have an initial velocity that's equal to negative the magnitude v naught, and we have acceleration, which is positive g. Okay, so if I were to plot this, first of all, would it be concave up or concave down? Well, remember that when we have positive acceleration, we expect our graph to be concave up. And so here I would expect something that would look kind of like a U. And that is in fact what I get when I graph my position versus time. So you might be wondering, why is my position getting smaller? Why is it getting lower from its initial position? Well, remember we defined upwards to be the negative direction. And so at the peak, it's actually going to be at, you could say it's a more negative value. And so it's actually going to be lower on my position versus time graph, which is a little bit confusing, but it's just because we switched the conventional coordinate system so that upwards was negative. Okay, and so I get this U-shaped graph here, which is what we expect, and the peak is really this lowest point then on my graph. And so you can see it is in fact exactly halfway through the duration of the trajectory, right? So it's halfway between the total amount of time and the initial time. And you can see the nice symmetry in terms of both the t up and t down here, as well as the displacement up and down for our ball. Okay, now let's look at velocity versus time. We have constant acceleration, it's positive g, and so I would expect my graph to be a straight line with positive slope. Okay, and specifically that slope is going to be 9.81 meters per second squared. Okay, so I get something that looks like this. I'm starting at an initial velocity, which is negative, so it's at the bottom corner. I'll go through velocity v equals 0 right at the peak, so right at this point right here. And then I will keep going and I will reach a final velocity, which has the same magnitude as my negative initial velocity, but it's opposite direction, so now it's going to be positive. Okay, last graph to look at here is the acceleration versus time graph. Acceleration is a constant in time, and so I'm just going to get a horizontal line right at g, or 9.81 meters per second squared. Okay, so that's a wrap on chapter 2, and next up we'll be taking a closer look at vectors before we move on to kinematics in 2 dimensions. I'll see you in class.